Sairam, having seen various reactions of aldehydes and ketones, it is now time to study about carboxylic acids, its properties and its various reactions. And the moment we come across this word carboxylic acid, we first need to study about the acidity of these compounds, because acids are something that are associated with acidic components where the talk about pH and other factors definitely come into play. So, in this segment now we will study about the acidity of carboxylic acids, which of them are strong, which of them are weak, why they are weak, why they are strong, all these answers we need to find. So, let us see what are the major aspects in this study here, where for a simple starting reaction, suppose if an acid is treated with a metal like sodium. Now, what does a metal like sodium do here is that the carboxylic acid has a general formula RCOH, and that is treated with a metal sodium, we get its corresponding sodium acid salts. So, this is the salt which is generated where sodium replaces hydrogen and then hydrogen goes out as hydrogen gas, because gaseous forms they generally are diatomic in nature. Now, we need to balance this reaction, so definitely I will take everything as 2 so that I can analyze that it is a balanced chemical reaction. What we can understand by this is a presence of a metal can get away hydrogen as H plus, and by Arrhenius theory, Bronsted-Lowry theory as well as Lewis theory, we have already seen that these type of acids are determined by how much of H plus is being generated by these systems. So, similarly you are able to see other reactions where sodium metal, sodium hydroxide and sodium bicarbonate are used. The main product is the sodium salt, sodium carboxylate. You could be getting other byproducts like hydrogen gas, water, carbon dioxide, various other forms can be obtained. So, if this is about mainly cutting of the OH bond which is present in these cases. So, what happens once you cut across the OH bond, what does happen to this ion which has been formed? So, this carboxylic acid which is RCOH, the moment you get away one of the hydrogen atoms which is present here, it tends to form RCOO minus, where the oxygen contains C double bond O, and here this side is C single bond O, but because hydrogen is gone out as H plus, it can form as RCOO minus. Now, this RCO minus will not retain in this state only, because to this carbon there are oxygen atoms which are attached together, and therefore, there could be a shifting of charge like this, where the negative charge on one of the oxygen can be shifted to the other oxygen which is present, because both of them are the same. So, this is what we call it as resonance. If you remember the resonance structures of benzene ring, basically they were undergoing a certain process of transfer of electrons, but finally the same structural properties were obtained. So, together what we can write this is as Rc, both oxygens are connected to carbon with a single strong bond, and the other pi bond which is there and the negative charge is actually fluctuating between the two oxygens. Writing dotted line parts a circular, semicircular aspect like this with a negative charge indicates that this negative charge is fluctuating between the two oxygen atoms which are present. So, this is nothing but the stabilization which has been caused due to removal of hydrogen atom, and there this sort of a stabilization can give acidity to the compounds, because we always know that better stabilization will retain to higher stability, and if RCO minus can be stabilized better, H plus production can be much easier. So, having known this resonance structures which are there, we will now study how a strength of an acid is being determined. Now, suppose if we have this as HCl which is being dissociated into H plus and Cl minus. This is a simple inorganic reaction, but the same thing if I consider an organic reaction, CH3COOH. This I can show it as a reversible form because this is a weak acid, and this is how I will be showing the splitting as CH3CO minus H plus. Now, we tend to write the equilibrium constants for this Ka. This is something which you have studied in first year equilibrium chapter, where for a reversible reaction the dissociation will be equal to the products, the concentration of products. Here my products are the CH3CO minus ions and H plus ions divided by concentration of reactants that are present, and I only have one reactant which is present. Now, this means that the more the H plus, as the number of H plus ions increase, it indicates that the acidity of the compound is also increasing. H plus indicates the strength of acid. So, if more H plus has to be formed, it means that the Ka value will also be increased. This can be understood by the mathematical implication also, where if this is numerator and denominator, we know very well that if numerator increases, final value increases. If denominator increases, because that is a divisibility factor, then the value will definitely decrease. So, since this is directly proportional, Ka is directly proportional to H plus, increase in H plus concentration indicates the increase in Ka, and this Ka can be related to a logarithmic factor where pKa is equal to minus log K. Now, since this is a negative logarithm, we now have to form a chain of thoughts between these. More H plus indicates more acidity, K is directly proportional to H plus, so more K indicates more acidity. Since this is negative logarithm, lesser pKa value indicates more acidity. Let me repeat this entire thing once again, where H plus production, if it increases, more of H plus indicates acidity. And since this is directly proportional, if H plus increases, Ka also increases, and that indicates that high value of Ka means it is more acidic. But when I correlate it with pK, which is nothing but power of the dissociation, we have already studied about pH, which is power of hydrogen. This is power of dissociation of an acid, Ka. So, since this is negative logarithm, an increase in Ka means that pK value will decrease. So, lesser pK values indicates that these are more stronger acids, and that is what is being put up here in points, that the strength of an acid is generally indicated by its pK value rather than Ka value. It is more of the understanding and easiness for us to represent it in various forms. Smaller the pKa, stronger the acid, that is what was conveyed to you. So, very strong acids will have pK value less than 1, moderately strong acids between 1 to 5, and weak acids they are above 5. Now, what does this mean that weak acids have pKa between 5 and 15? Generally this pH factor we talk between 0 and 14, and we say that above 7 is base. Now, here this is not pH or pOH, this is pKa. So, high values of pKa indicates that the acidity of the compound goes on decreasing. So, what happens here if there are other groups that are being present in these cases? This can be understood by an example where I am going to take propanoic acid, because 3 carbon systems are there. So, propanoic acid, and to this propanoic acid let me take another example, which is CH2COH. This is nothing but the presence of fluoroethanoic acid. If I want to take a similar example, I can also go for fluoropropanoic acid. Now, the question is, among these two, who is more acidic? Now, that will depend on how best the H plus ion can be dissociated. In this case, we can see that CH3, CH2, COO minus plus H plus. Here, electron donating groups are there, CH3, CH2, which means that they will increase the electron concentration in this region. The moment they increase electron concentration in this region, breaking of this bond will be pretty difficult, because to obtain acidity, breakage of hydrogen ion is a must, and If massive electron concentration is there, breaking that is difficult. But what happens here due to presence of fluorine is, we know very well that fluorine are electronegative compounds, and electronegativity indicates that they attract the electrons inductively, which indicates that the electron concentration in this region is comparatively reduced. Why it is reduced? Because an electron withdrawing group is attracting the electrons. So, when the electron concentration is reduced, getting away H plus will be pretty much easy. So, when they ask such comparative study, the effect of an electron withdrawing group and electron donating group matters. So, in this case, let me take another example where FCH2COOH. If this part is my main part of discussion, what I can say here is that to this group there is an electron donating group, which increases the electron density, thus making it difficult to break the bond. To this, electron withdrawing group is added, and that electron withdrawing group can attract the electrons, therefore very easily H plus can be given out. So, here the effects of electron donating and electron withdrawing are being explained, where electron withdrawing groups will increase the acidity of carboxylic acids, because they are able to stabilize the compounds, because they are able to withdraw the electrons, and therefore release of H plus is becoming easy. But same way, if you have electron donating groups, they will supply more of electrons, and their conjugate base will be correspondingly destabilized. So, considering these factors here, we have a series of compounds which are there, and in the first place the effect of the groups on acidity are considered. That is mainly because of the consideration of electronegativity, where pH and then iodine, bromine, chlorine, fluorine. Why that order is followed is because we know very well that the electronegativity decreases down the group. So, naturally iodine will be less electronegative, then bromine, then chlorine, then fluorine. You can see CF3 at the end, because 3 fluorine groups can act as electron withdrawing group, and thereby they can attract the electrons very easily. So, this is a complete table study as such. You can employ the same factors, where the first two compounds, if you see, CF3COOH is more acidic than CCl3COH. The reason being F is more electronegative. Make a comparative study between second and third compound. In the second compound, 3 chlorine groups are there. Third compound, 2 chlorine groups are there. So, higher number of chlorine groups, or to say higher number of electron withdrawing groups, will naturally give it more acidity to the compound. If you see to the fag end of the series that has been present, in the fag end you generally have this aliphatic carboxylic acids, because methyl groups CH3, CH2 and all these type of groups are basically electron donating in nature. So, this is the acidic strength of some of the acids which have been present. And what about if they are aromatic acids? Do they play some role in the acidity of the compound? Definitely they will play some role in the acidity of the compound, where the moment we go for aromatic acids, the best example is going to be benzoic acid, and the question is it acidic in nature? It will definitely be acidic in nature, because when we dissociate this compound, if we try to dissociate this compound, benzene ring COO minus and H plus. How can we judge whether H plus is given out strongly? That is just by stabilization of this negative charge which is present, and stabilization is definitely possible because this resonance can happen even in benzene. We know very well that benzene undergoes various resonance structures. So, the more the resonance structures, the more the stabilization. So, therefore, benzoic acid will definitely be one of the very important acidic compounds in these cases. And this is also already, you have seen it in the earlier series which was seen, that benzoic acid, if you especially see the last column which is present, benzoic acid, that is C6H5COH, was present at a higher acidic range when you compare with the other aliphatic acids which are present. Now, here both the effects can be obtained in these cases. So, what we are going to do now is take a comparative study of various benzoic acid molecules which are present, and those are generally the substituted parts, where in the first case I will take the benzoic acid, where I am going to substitute it with an electron donating group. OCH3 group is methoxy group. This is electron donating because electron concentration is very high here. For a comparative study, let me again take benzoic acid, in this case COOH, and then let me take another compound where an electron withdrawing group is added, and the example let me take it as NO2. We know very well that NO2 is an electron withdrawing group. Now the question is, which among this is most acidic? First things first, how are you going to decide the basis for acidity? Acidity basis is determined on the fact that the release of H plus should be easy. Whoever can release H plus easily, they will definitely be most acidic in nature. The question here is, will he be able to release H plus better or this person? COH will definitely be in between because this is the base compound, whereas here you have an electron donating group, electron withdrawing group. Now an electron withdrawing group can withdraw all the electrons towards itself. So how does it withdraw electron towards itself is, all these NO2 groups which are there can act as an electron withdrawing system where as much as possible it will reduce the electron density near the COH group. But unfortunately OCH3 will rather supply electrons to the benzene ring and therefore increase the concentration of electrons, and therefore release of H plus there is pretty much easy. And this is how we can say that with more H plus being released in those cases, the acidity of an electron withdrawing group presence is definitely more suitable for the study of acidic compounds, where these electron withdrawing groups will withdraw electrons, reduce density, and H plus release will be pretty much easy. That can also be seen in the pK values that are being shown here, where 4.46 is the pK value for 4-methoxybenzene. For benzoic acid you have 4.19, whereas for 4-nitrobenzoic acid you have it as 3.41. We have already seen that a lower pK value indicates more acidity of the compound. And the other reasoning we have seen, where the presence of an electron withdrawing group will definitely make it more acidic due to easy release of H plus ions. So this is how the acidic strength of various compounds can be studied, and comparative studies of these acidic compounds can be done. So having gone through all these parts here, we have a small assignment, explain Clemenson's reduction, a very important named reactions. So generally when we tell explain, you got to write the reaction and also make a small explanation about the catalyst that you have used and the reactants as well as products. Write the reaction for the aldol condensation of ethanol, which among ethanoic acid and propanoic acid is more acidic and why. Again, the comparative study of the presence of electron withdrawing groups have to be considered. What is the effect of the presence of electron withdrawing group in a carboxylic acid molecule? So consider any carboxylic acid molecule, COH group, if you can just consider, and then see if there is a presence of electron withdrawing group. What effect will it do? Will it raise the acidity or will it decrease the acidity? So this is all we have for this segment of the study of acidity of carboxylic acids, and hope you have been able to assimilate all the concepts that were told here, and definitely practice makes you better. So you can look out for various other compounds that have been present, and you can try to make that correlation study where we can consider the release of H plus easily and determine which is more acidic, which is less acidic. Thank you. Sai Ram.